Hello, number 2, the discovery of helium. Let's just quickly recap a little bit about what we learnt in the last video, and the main thing that we need to know in case of this is absorption spectrum and a line absorption spectrum, and that's when white light passes through a vapor or a low pressure gas. The photons of the frequencies corresponding to the line emission spectrum of that gas will be absorbed. So you get characteristic lines depending on the elements that are absorbing the photons. And that's what we're trying to show here. So if we looked at the solar spectrum, in which case this would be all nice bright rainbow colors, but there'd be these black lines because the gases are absorbing these photons of these energies that correspond to these energies, remembering E equals HF. So every photon has its own characteristic. Every photon with its own frequency has its own characteristic energy. And then the atoms absorb the photons for these frequencies, but then re-emit them in all directions, and therefore you have a diminished amount in those areas. And we fleetingly talked about band emissions or absorption, but don't need to worry about that too much. So pause that and have a reread of that if you like. Now, what's that got to do with helium? Well, this is the solar spectrum here. Some of it's hidden behind me. But if we looked at the solar spectrum, you'd see the colours of the rainbow representing all the possible frequencies, but there'd be all these black lines. And people had known about that for some time. In fact, when was that discovered? That was discovered many years before helium. And however, the spectroscopic evidence for helium was attained in 1868. During a solar eclipse, and the solar eclipse allowed them to decrease the amount of light coming from the sun, so they could actually concentrate on what was coming out of the gases of the sun or the corona of the sun, rather than the whole sun itself. And it was by Lockyer and Janssen, and they both were studying it during this eclipse, and they both came up with the presence of helium. And that's what they look like. That's Lockyer, hang on, and that's Janssen there. Okay, so what they observed was a bright yellow emission line was observed and was later shown to correspond to no other element. And so what they did, if we went back, let's go back. People, all these lines, what they had done is they'd sampled all the elements in the periodic table, put them through various flame tests and things, and looked at their spectral lines, and then these guys and everyone else who was working on it at the time subtracted all the known elements off these lines. And in the yellow area there was one line that was unexplained by all the known elements, and these guys concluded it must be a element that is not known. And the element was named, and Lockyer and Franklin, who was working with Lockyer, named it Helios for the Greek letter or the Greek word the sun, and Lockyer got knighted for it. Franklin didn't. I don't know why. Might be interesting to find out why. And that's Lockyer again. And helium, so it was discovered and named, but it wasn't actually isolated to 1895, so many years later. And it was difficult to isolate because it's a noble gas. And it had to be isolated from a sample of uranium metal by Sir William Ramsay. And that's what he looked like. And effectively, just to recap again, what they would have done, now this is using a gas discharge of hydrogen, but what they would have done is filled it up with helium instead, shone the light through there, through a narrow slit so you get a beam, put it into a prism, and separate it, and they would have observed the line spectrum, and the line spectrum would have corresponded for helium. So what we need to do, let's look at an animation of a discharge tube. So I'll just bring it up. Let's hope that this works. There it is. So here we have our evacuated tube, and we have our plates where there's an electric field between the two, and we're sending a potential difference across the two. We'll heat up the plates, and there we go. So the plates are heating up, electrons are getting boiled off, they're finding themselves in an electric field and they're accelerating. They're hitting this case, in which case it's hydrogen. These are the energy levels of hydrogen, which we haven't really done yet. But what you'll see is, let's boost it up a bit. So we heat it up, lots of electrons coming off, and what you're getting is building up a let's just increase the energy as well to max out. And what should happen is these guys, these are getting excited, and then the electrons are dropping back to their ground state, giving off these other photons, and these photons correspond to these different wavelengths as they drop back from the energy shells, and we're building up the spectroscope like this. Now what we could do is we can do multiple atoms. Okay, makes it a bit better. Zoom it up, add the spectroscope, and increase the power, and there's the spectrum for hydrogen appearing. And if we move to something else, for example mercury, different atoms have different energy levels, and therefore we'd get a different spectrum coming off. And let's just do neon, and there you go with neon. So this will be on the OneNote, so have a play with it. Lots and lots more happening than this, and we might actually look at it sometime in class. Okay, so I can get rid of that. Let's move on, and we will be looking at discharge tubes or lamps with the spectroscopes. And in the next video we'll actually be looking at those energy levels, how they're formulated, and what we can do with them. See ya!